Dr. Zaniewski here today to give us some insight on the asphalt. He's the author of our textbook. I got mine signed. You guys can do the same if you get up here quick enough, I guess, before we get out of here. Get out of here. Tear it up now that I've got it. Now it's valuable. I tore it up. There goes the value. There goes the value. I don't have a bio to do a great introduction, so I'll have to let Dr. Zaniewski do that himself. And then he's got a lecture, of course, on asphalt and bonds and that kind of thing. And I think he's got some other things he's going to talk to you guys about after he's done with the lecture. So please pay attention, ask some good questions, make me feel proud.
Okay, just real quickly, Zaniewski is an intimidating name. It's not a hard name. Okay, 3 syllables, Zaniewski. And if you ever have to spell it, I before E. Okay? I'm the asphalt technology professor at West Virginia University. What that means is I get these fancy things to wear. Okay? My position was created by a grant from the Asphalt Paving Association. They looked at it and they said, "You guys aren't graduating anybody that knows squat about asphalt." Well, is that important? How much construction do you do in West Virginia? Any ideas? Ideas, I watch Orange County Choppers. A lot. No, we don't. Compared to other people, we don't do much. But we do about $1 billion, so if you can get 10% of that, you're feeling pretty good. About $1 billion worth of research. That's a couple years ago. The highway department does about $750 million of that billion. Of that $750 million of that billion, about $500 million for this stuff. What do you think the chances are in your engineering career that you're going to get involved with this stuff? Somewhere along the line, it's pretty good. You design a building. Turns out that in our society, we like to park close to the building. This is good stuff for parking lots. We like to drive to the building. This is good stuff for streets. You live in a residential area. Your neighbors say, "You're a civil engineer. We need to repave the roads. You help us." Okay? So it's a tremendous part of the American infrastructure. How many miles of roads are there in the United States? Yes. About 4 million miles of roads in the United States. How many of those are paved? And this is a number that people go, "What?" About 2.2. Almost half of our system is unpaved. Okay, but we're going to, but the part that's paved is carrying like 95% of the traffic. You know, the Forest Service goes down out and knocks down 3 trees and calls it a road. Okay. Okay, so we're down to like 2.2 million. Out of the 2.2 million, what do you think the asphalt is?
1.5.
What?
1.5.
1.5. Probably about 1.9. It's in the 90% depending on the state. West Virginia, 38,000 miles of road, 23,000 miles paved. The only concrete we have now is a little bit of new stuff that's being built, like 9 miles. And parts of the interstate where they haven't corrected their mistake of building the concrete pavement by overlaying it yet. So most of our interstate is overlaid, right? So if our 23,000 miles are probably up in the 22,000 mile range of asphalt. Okay, so it's a big deal, important topic. Okay, now what is asphalt? Well, it's a hydrocarbon. Oh, I normally do about 6 lectures on this for my class. I'm biased. I think it's that important. I'm going to do it 1 lecture today, right? So you're getting the Reader's Digest version. Now, I had 2 choices when I'm making up the presentation. I could talk either really fast and cover 6 lectures worth of material, or I could be selective on what I put in. I elected to be selective. You're getting the Reader's Digest condensed version. What we're going to talk about is the materials, the asphalt, the aggregates, that's the structure that carries the load. The aggregate is the binder, or the asphalt's the binder that holds it together. And when we mix that together, we call it asphalt concrete. Normally, when we say concrete, we think of that white stuff that's made with Portland cement, right? But correctly termed, that's Portland cement concrete. cement? Okay? Cement just means some kind of gluing material, binding material. So asphalt cement. Now one of the issues that we have is we have to take the word asphalt in context. Because sometimes we use the word asphalt to mean the asphalt cement, and sometimes we use the word asphalt to mean the asphalt concrete. So if I ask you what kind of parking lot is out here, you say it's asphalt. That's what's it made out of? Asphalt cement plus aggregate. So it's correctly it's asphalt concrete. Two main ingredients that we put in there are aggregates and the asphalt or the binder. And then the third thing that we need to carry in there is air. Now, if you studied the concrete chapter already? Yeah? Okay. In the concrete chapter, what did you learn about the importance of air?
Workability.
We can get workability the other way. Freeze thaw protection, right? Concrete basically would not work in an environment where it freezes if we didn't put air in it. Asphalt doesn't work very well if we don't make sure we got the right amount of air in it. Okay, so it's kind of a little parallel there. And then we'll cover a little bit about, so we'll talk about how do we, one of the main roles that we have as civil engineers in this field is deciding what proportions of materials, asphalt, binder, aggregate, binder, and air to put together so it's a good asphalt concrete. Now just putting that together doesn't do us a whole lot of good until we go out and we build with it. So we'll spend a few minutes talking about the construction process, proportioning and mixing, transporting, placing, compacting, and quality control. Okay, so chemically, asphalt falls under this broad category of something called bituminous materials. And bituminous materials come in two flavors, the asphalts and the tars. They come from two different sources. Tars are created by destructive distillation, so they're not part of the petroleum tree. And asphalts basically come from petroleum. We're only going to, well, people that aren't as informed as us, you know, people that call concrete cement, you know, when they, that's the gray powder, you know. And I used to laugh at them, but now I just write it down and go home and laugh in the closet. I kind of more socially acceptable. So we have the same situation with asphalt and tar. If you talk to some of the guys out on the road and they say, yeah, we're putting tar around today, well, no, they're not. They're putting down asphalt. We haven't used tar for roads in the United States for, I don't remember it. Heck, that's a long time ago if I can't remember. Okay? So we're going to talk about the asphalt, and it can come from either a natural source or a refined source. And when I was studying, the textbook we used had about equal amount of representation for natural stuff as refined stuff. And it turns out that when we started building roads, the natural stuff was out there, and there's this big lake in Trinidad that instead of having water has asphalt. And so they go out there and they slice off chunks, literally, put them on a railroad car, take them back, heat them up so they can get rid of the sand and the water that's in there, and sold them. And if you look at a lot of references that are historical about asphalt, that say that Trinidad Lake asphalt was the first asphalt used in the United States. There are historical documents in Ritchie County, West Virginia, that the first asphalt pavements built in the United States were made with Ritchie County asphalt. Really good source of asphalt, just a slight problem is it's also intermixed with natural gas, so when you go in there and you start swinging a pit and you hit a rock, you kill people. And then once they lost enough people, they decided to stop doing that. So the natural stuff is well under 1% of the market. Everything that we're going to use and talk about is basically refined from petroleum oil. Okay? So that's the one we're going to focus on. Now when we refine it, we can break it down into the asphalt cement, an emulsion, or a cutback. If we had the full 6 weeks, or 6 lectures, we'd talk about the other 2. But since we're focused today, we're only going to talk about the asphalt cement. Okay? So we say it comes from petroleum. You pump this stuff out of the ground, you run it through a still. You all know how still works? Yeah? Usually when I ask that question in other states, I got to explain how still works. It seems in West Virginia, everybody knows. Okay? And so we get all this other stuff that came with petroleum, and see, we use code words, light solvent. You know what the light solvent is? Yeah. What do you get out of petroleum oil that you really like? Stuff you bought recently, gasoline, right? So we don't want to say, oh, it's gasoline, because this is stuff we want, right? But you get rid of the light materials, gasoline, diesel fuel, fuel oil, lubricants, etc. And what you're left over with is the asphalt cement. In fact, it used to be called the bottom of the barrel. Where was the first oil well in the United States? Titusville, Pennsylvania. What did they want oil for at the time? Before cars. What was the big energy need? Lamps. Lamps for lights. Okay? But you say kerosene, but they had lights before that. What was the energy source for the light they had before kerosene? Whale blubber. And so in order to have a sufficient number of lights, we were killing all the whales. And then somebody figured out, oh, there's this stuff, and it'll light. But you don't want to have something that burns really fast if you're trying to make a light, like having a flame. So they wanted the kerosene. So they ran the oil through the still, and they retrieved the kerosene, which is more of a medium weight, and they got the gasoline. And back in the day, if you had something like gasoline that you had absolutely no use for, of course, where'd you do it? You threw it out. Where'd you throw it out? Because you didn't want it sticking around, you didn't want to pour it in front of your door. You wanted to pour it somewhere where it would go away. Yeah, so you just pour it in the river, right? That's where we were, okay? Now, we've gotten to the point where most of the petroleums that we produce have asphalt in them, but the darn chemical engineers have figured out how to break down this valuable hydrocarbon for building roads into making alternative products like plastic. And since you can sell that for more than you can sell the asphalt for, only about 25% of the refineries are now making asphalt. So that's what we're using for our road building product. It also has other applications, but in the condensed version, we're not talking into it. Asphalt cement has some nice things. It adheres well to most rocks. Some rocks it doesn't adhere well to. We got to test for that when we're designing our mix. It's waterproof. Asphalt and water are immiscible materials. That's your fancy word for they don't go into solution. It's pretty durable if we build the pavement right. It's resistant to acid, alkalis, and salts. And this thing of people saying, oh, I put the road salt on my asphalt driveway and cause problems. And the asphalt wasn't put in right. Salts will tear up concrete, okay, but they shouldn't tear up asphalt if it's done right. And then it's very temperature sensitive. A material that's temperature sensitive and flows, that would be a viscous material, right, as opposed to our solids like steel and concrete, right? That makes it a tricky material to deal with. All right, so what we're going to do is we're going to build a pavement. The wearing course is for sure going to be asphalt. If we're talking asphalt pavements, it could be concrete or it could be gravel, but 92% of them or so are asphalt. The base can either be a granular material, the sub-base can be a granular material, or we can try and build a really strong road by building full depth asphalt pavement. So we can use the asphalt all the way from the grade up to build our best quality roads. And that's pretty much the strategy that the DOH is currently implementing. We didn't know very much about asphalts for a long time. And then there were some pioneers that came up. One of the pioneers was a guy named Bruce Marshall. Had nothing to do with this other Marshall Jew that's somewhere around here. And he was an engineer with the Mississippi Highway Department. And he was one of the guys that figured out how to proportion asphalt and aggregates to make asphalt concrete. There was a big highway research bill funded, and they said, we need to do more research. At the point, you got the transportation system that's the lifeblood of any economy, especially ours, and the amount of capital that was being put into research to maintain and make the system better was less than what was being spent on the garbage industry. You're filling you're paying more money to figure out better ways to get rid of your trash than you were to figure out how to haul your trash away. Okay? And so they developed two things that are of significance to us. One is a mixed design process called superior performing asphalt pavement, SuperPave, and the other is a performance grading method for asphalt binders. So we're going to talk about that for a minute. Now, way back in the day, to show you how primitive the technology was, an asphalt technologist would pride himself, and excuse me ladies, but none of you are crazy enough to do this, so you should be excused, would pride himself on his ability to take a chunk of asphalt and stick it in his mouth, chew on it, and tell you whether or not you could build a pavement with it. Okay? So we progressed from that. We now have specific performance tests that we want to do to grade the asphalt material. So this is the asphalt material. If I took this tin and I just laid it on its side, it could sit there for a couple of weeks and it wouldn't escape the container. If I stick this in an oven and I heat it up, starting about 180 degrees, it starts to flow out of the can. I heat it to 300 degrees and it starts having a viscosity kind of like mineral oil. Okay? A little bit lighter than 30 weight oil for the product. Okay? So if you're interested, I'll just pass this around you. Try and poke it. If you really want to involve yourself in the lecture, you can actually pull out a chunk and chew it. Your choice. You'll notice that nobody's actually taking me up on that offer. Okay? So that's the binder. Now, you would expect binders, high quality roads in cold climates versus roads in hot climates. You need different asphalts for that. Okay, so we've got to have a way to figure out that and grade it. So that's the performance grading system. Now, if you're going to buy something, you ought to buy it to do specific things. So what we want to do is look at the asphalt's contribution to distress. Okay? And so the three primary distresses that we concern ourselves with, that we can identify a role of the binder in resisting, are rutting, permanent deformations in the wheel path, fatigue cracking, flexing of the pavement until it breaks, and thermal cracking, where the temperature drops, the volume of the material reduces, and yet it's on this long ribbon, so we're not letting the road actually reduce in length. And so if you want to reduce in length and you can't, you get stressed. Right? So that's the three. Now, because of the nature of asphalt, we have different condition states of the asphalt. We have the stuff that we bought from Marathon Ashland, somewhere that way, over in Kentucky, right? That's the tank asphalt. They bring it out to the plant, and then what we do with it in the plant is we heat it way up. And if you ever want to increase the rate of a chemical process, the two things you do is you add heat and you maximize surface area by spreading it out, right? If I spilled some water on the table, which wisely I don't have any water because I've done this before, and I want to get that water to evaporate, I could put a hair dryer on it to add some heat, move it with some air, and spread it out so it's got more surface area. Well, what we do in the asphalt plant is we heat the asphalt up to 300 degrees and we spray it down onto the aggregates, and then they wind up having a surface coating of about 9 microns, so it's a pretty thin layer, and we have this heater in the asphalt plant that's blowing air through it. So we rapidly oxidize the asphalt in construction, then we take it out, put it on a job, slam it through a paver, hit it with a roller, and say, done. And then it lays out there in the sunshine and the oxygen, and that changes the characteristics of the asphalt. It ages. Okay? So we've got three states that the asphalt's in. The tank state, the construction state following it, and this is where I got to do my quality control, right? Unless I've got a really long-term warranty on the project where the contractor has to pay to fix it, very rare. As a highway department, the main purchaser of this product, I can only test it right after construction, right? So I want to make sure it's got the right properties right after construction. But what happens is the viscosity continues to increase. If you pick the layman term to describe an increase in viscosity, do you want to try and pick one, or do you want me to say hardening? It's your choice. Okay, it's hardening. Okay, and it's caused by chemical changes, we get the short-term stuff in the construction process and the long-term stuff in the use of the product. And we say this this happens like within hours, because from the time you heat it up in the plant and you get it put on a pavement, it's a short period of time, hours at the most. This happens over 8, 10, 12 years. We can't really say is it 8 or 10 or 12 years because the curve gets real flat. And so there's not a big difference between 8 years and 12 years. Okay? Okay. So then we're going to buy this product. How are we going to test it to make sure it's got what we want? Well, there's a whole series of tests. The purity test dates back to the days of the Trinidad Lake asphalt. It had sand and water in it, and if I was paying $150 a ton for asphalt cement in a time when I could buy a horse for $3,000, I would think that that's very expensive, and I want to make sure I got a pure product. So you just basically take a cup, put the asphalt in the cup, wash it through a filter. The stuff that's left over after you've washed it with the solvent is sand usually, and so you don't want to be buying sand at asphalt prices. So it's pure. Since we've gone to petroleum-based products, I've never talked to an asphalt technician that's done this test that had one fail, and yet it's still in the specification. Say if you're going to heat this stuff up to 300 degrees, it's coming from a plant that's producing gasoline, kerosene, diesel. All these things burn. You know, gasoline's going somewhere around 170 degrees. You get gasoline to 170 degrees, you can catch it on fire pretty easy. So if you have a contaminated asphalt, boom, you burn down your asphalt plant. Now, they never allowed me to research this, but I'm pretty sure that's not good. Viscosity at 300 degrees or so, and we do the test at 275 because that's kind of like the minimum you ever get. We want to be able to pump it, we want to be able to mix it with the aggregates, and then we want to be able to compact the sample. So we measure viscosity. Then we have a couple of other tests that are kind of harder to explain, but modulus is what? In the engineering world? Ratio of stress to strain, elastic modulus? Okay. In the world of viscous materials, we use shear modulus, which is shear stress over shear strain, okay? And the problem is that they don't line up at the same point, and so we've got to have this phase angle thing happening with our asphalt. And so we would go into that in more detail, but today you're not getting full coverage. This test is used to evaluate the material for the rutting and the fatigue characteristics. Then we also want to check for thermal cracking, so we've got 2 more tests for that. 2 places in the state have the second number 2. I'm gonna have to work on my count. The third one, and the fourth one, my lab and the DOH. The DOH has number 5, the direct tension test. When I was putting together my lab, it turned out that the machine that they were selling was a better random number generator than a measuring of materials, and so I didn't buy one. They've since refined the test, but I ran out of money. Viscosity, flow. When we are mixing the asphalt with the aggregates, we want it to flow and coat the aggregates, and then when we try and compact the stuff, we want the asphalt to act as a lubricant to allow the aggregates to slide past each other to get in a dense configuration. And if I just went out and I took different asphalts and I heated them up to the same temperature, they would have different temperature viscosity curves. And so just heating it to a constant temperature wouldn't bring all the asphalt back to the same ability to flow. So the specification is we got to do our compaction and our mixing at certain viscosities, and we measure that with a rotational viscometer. So that's an important part of the lab process. Performance grade binders, we're going to try and eliminate permanent deformation, which is the correct term for rutting, fatigue cracking, low temperature cracking, and we also want to make sure it doesn't age too much, and we want to check for pumping and handling. When we go to buy some asphalt, it's today, because the manufacturers got together and said you can use the old system air, but we only want you to use one. The new system is called the performance grade system, so it starts with the letters PG. Then it's got two temperature designations, and they're basically based on the highest anticipated temperature of the pavement and the lowest anticipated temperature of the pavement. So you establish your range, and then if your highest is 61.3, you can't ask the manufacturer to make 61.3, right? Like in men's pants, you don't get, they come in 2-inch sizes, you get 32 or 34, you don't, well, never mind. You can't get a size 33 waist men's pants, okay? So you can't get exactly what the temperature is, so you specify a temperature that's above your highest and below your lowest, and they come in 6-degree increments. The standard grade of asphalt that's used in West Virginia is called PG 64 minus 22, and those are in Celsius. 64 degrees Celsius, is that hot? Way hot. The hottest I've ever been just in an open environment was 43 degrees Celsius, and that was in Phoenix. I was driving by the airport. They announced it's 123 degrees. At the airport, they shut down the airport because their temperature takeoff charge only went to 120. And I was driving by in my 67 Mustang with the heater broken on position. I no longer have that Mustang because my mother-in-law burnt down my house on Valentine's Day and the car was in the garage, but that's another story. That's another story, okay? So we don't get that hot, but sunshine sitting on a pavement gets that hot, okay? So, you go out and you walk barefoot across the pavement in the summer, you go, shouldn't have done that, right? About the fourth time you start figuring out where something is or something, right? 22, do we get that cold? Oh, that's Celsius, right? What's 22? 22 we basically divide by 2 is minus 11, and we add 32, so we get a little colder than that. Okay. But again, that's pavement temperature. You're probably thinking air temperature. Pavement's always stay hotter than air. Okay. So that's what we use in West Virginia. Then we're going to mix it up and we're going to make asphalt concrete. Okay, so if you haven't ever actually gone out and embraced asphalt concrete, it's your opportunity. It's cool enough that it shouldn't be dirty or anything. Asphalt, aggregates, and air. And so there's some statistics that we've already covered. We figure out how to do it, and then we mix it up in the central plant and go out and pave with it. The things we want are stability to avoid the rutting, resistance to flexing or fatigue cracking, resistance to thermal cracking, and see, there's a compromise. The things you do to improve rut resistance reduces fatigue and thermal cracking resistance. So it's always a compromise. Resistance to age hardening, thicker films help that, and so that's opposite of what you want for rutting. Moisture-induced damage, where your glue doesn't stick to your rock very well. We don't have that problem in West Virginia, but Pennsylvania does. And I don't know what happens to the concrete when the Pennsylvania contractors come across the border and build it in West Virginia. Skid resistance, that's our ability to do nice things in an automobile, like accelerate, go around corners and stop. I'm an asphalt technology professor, actual and factual. My godfather, well, I had nothing to do with picking him because I was kind of young at the time, made his living back in the early 1950s, going around the country doing lectures, asphalt pavements, black ribbons of death, because we hadn't figured out how to provide skid resistance with asphalt pavement. We now do it through a specification on the aggregates to keep them from polishing so that we do get good skid resistance. And then if we can't build it right, it's not going to perform right. And then the last thing is, as always, we need an economical mix. What you're mixing together, asphalt, aggregates, and air. Which one's the most expensive? Asphalt. So if you want to have an economical mix, what would you do? Minimize asphalt content, right? bid this job, I'm gonna have to be the low bidder. The mix types are based on the nominal maximum aggregate size. That was covered in the aggregate chapter. Y'all remember that? What is nominal maximum aggregate size? Can anybody tell me?
One size larger than the first.
To retain at least 10% of the aggregates, right? There's two definitions. This is the one that's used in super bid. We make, what is it, 1, 2, 3, 4, 5, 6 different mix types are available to make. The 470, these are based on the nominal maximum aggregate size, and it's millimeters of sieve, so the number 475 sieve is number 4 sieve. How big is the number 4 sieve? What is the number 4 sieve?
I think it's 4 C's per inch, right?
4 what?
4 C's per inch.
4 openings?
Yeah, 4 openings
per linear inch.
Yeah, per linear inch.
So it's a quarter inch.
No, it's a little bit less than that.
How little?
I don't know.
I mean, you're on a really good roll. I shouldn't be beating you. I should be beating somebody else who's not participating.
It's not a quarter inch because you gotta take into account.
Who's got wires?
Yeah.
Okay, so it's about 0.18. And indeed, if you take the 475 and you convert it to inches, you'll get about 0.18. Very good. Okay. We use that on some maintenance, but the primary ones that we use in West Virginia are the 9.5, and just about everything you see is 9.5. 12.5 is becoming more popular as they've gone to thicker lifts, and there's a reason for that we have one time we cover. 19 is done for base, so if they're out on an interstate job, they mill off the old job, they put down 2.5, 3 inches of base. It's going to be a 19 millimeter, and then they'll usually come back with 1.5 inches of wearing, and that's probably going to be a 9.5 unless they've adjusted it. And then the heavy duty base, the big rock stuff, is used in base materials, and 37.5 inches is approximately 1.5 inches, right? Now it doesn't mean you don't have rocks bigger, right? They have to pass the 2-inch sieve, and you have some retained on the 1.5 inch sieve. And those there's some cross sections of what these different gradations look like. Okay. Now we have to decide how much stuff to mix together in order to make asphalt concrete. Now, since you're getting a Reader's Digest version, I thought I'd give you some Reader's Digest notes. Oops. Oh, I didn't see it. What? It's not a problem unless you're concerned about quality. If you want your tables to last, it's a big problem. Okay? And I'll talk about that in a minute. That's a very important thing. So the first thing, well, actually what I have on this sheet, these are actually kind of the steps that, once I figured out my materials, this is what I want. So this slide actually starts on step 3, where I selected a blend of aggregates that I'm going to use to make my asphalt concrete with. Once I've selected that blend of aggregates, I then select my design binder content or the selected design aggregate structure, and then I evaluate my moisture susceptibility. So we'll kind of step through that stuff. I've left down some slides where I got something misplaced. Stockpiles, let's go back and talk about the aggregates a minute. Stockpiles, that's out of the aggregate chapter. They're evaluated for source properties. Toughness, soundness, deleterious materials, those are evaluated for stockpiles. Consensus properties, and what we need is a lot of friction because we're going to get our, between the aggregates, we're going to get our stability from the rock. So that's the coarse aggregate angularity test and the fine aggregate angularity test. That's what tells us about friction. And then flat and elongated, if you've got these screwy sized particles in there, they'll break when you go to compact it. And sand equivalency test to make sure that it's clean material. Things we need to know are bulk specific gravity, parent specific gravity, and percent absorption. We'll cover those and the gradations. And then the and then we have to look at what happens with the blends. The binder we select based on temperature. So for West Virginia we selected a 64 -20. 0.2. And if we have heavy traffic, we bump that one upper temperature grade, 70 minus 22. We have slow traffic, we bump one grade. So if we're doing city streets, we shouldn't use the 64, we should use the 70. Yeah, and the word should was appropriately selected, okay? And then if we have slow and heavy, then we want to bump 2 grades. Anybody been to Fort Gay? Know Fort Gay? Heard of Fort Gay? Okay, it's just kind of to the south of here. Big coal haul issue, right? And some highway engineer went in and put in a traffic stop light. What happens when you put a heavy coal truck on viscous material? Yeah, so they started having really big rutting problems. The highway department was going out there and changing it every 3 months. That's expensive. 8 years ago, they built a project to replace the material in the intersection with a modified binder that was selected based on this criteria. They haven't been back to it. Probably spent about an extra 15% compared to what they were spending every 3 months, but it's been out there 8 years. I'm real cheap, but I would buy that one. Okay, we're gonna have to mix some samples and compact them. When we mix and compact them, we use something called the superpave gyratory compactor. And then when we compact the samples, they're going to have some air in it. So usually our term when we have something with air in it is bulk. So bulk specific gravity of the aggregates. We then want to know what would be the density of the mix if it had no air. So we make up some more sample. We get the weight, we put it underwater, and we use a vacuum to suck all the air out of the sample. Get the submerged weight, got the dry weight, get the maximum theoretical specific gravity. The difference between these 2 specific gravities, that one has air, this one doesn't. So I can use these 2 together to figure out how much air is in that one. Gyratory compactor, basically you put a vertical load on, you tilt it up, and then you rotate it. I don't know how this works. This is a great big stiff mold. The outside of the mold has to be an angle of 1.25 degrees, but the inside of the mold, they've got this special machine for measuring. It only has to be at 1.17 degrees. But that's the way it works. Okay. When we're going to compact it, we have we always use the same vertical force and angle of tilt, and then we vary the number of gyrations to vary the amount of energy we're putting into the sample. And we have 3 gyration levels that are used. They're called the end design. That's so that we compact it to what simulates construction, following construction. End initial is a number we pick off while it's gyrating to end design, and an end max is a measure of how much that asphalt will actually compact over its life, because we always want at least 2% air width. Now, we're going to get into here, and we're going to have to talk about variables in equations. This sheet didn't print right. So ignore the stuff that shouldn't be there and look at the stuff that's up here. X is our parameter, so those are things like weights, volumes, gravities, mass, and percent. And they're very conveniently chosen. If it's a G, it's gravity. If it's an M, it's mass. If it's a P, it's percent. Okay? The second digit tells us which material we're talking about. So we've got asphalt, aggregate, and air, right? And they're all A's. So that would screw us up, right? So in order to clarify that, A is for air, B is for binder, S is for stone. And then we're also going to talk about when we put them together, and we use an M for mix. Pretty straightforward so far, right? And then we have different modifiers on these terms, and so A is for apparent if we're talking about stone. So we have apparent specific gravity of stone, something covered in the aggregate chapter, and bulk specific gravity of stone. And if it's a G, if it's something B, A, then it's absorbed, and that's only for the binder, right? So you got 2 A's on the end, but one of them's only used for, so we have to know when we talk about stone, we talk about binder. B is for bulk, E is for effective, and M is for maximum. And so if you kind of look ahead a little bit, you'll see you've got an equation sheet here, and this equation sheet is totally useless unless you know the code, right? super pave mix design, this kind of is a more complete list of what we have on this design sheet. 5 elements: aggregate selection, binder selection, determine design aggregate structure, determine design binder content, and evaluate one for acceptability. So we'll just step through those processes. On sidebar, because of segregation, we're going to design mixes that have a blend of gradations, but in order to maintain a consistency in that blend, we're going to stockpile our aggregates to where we just have one size in each stockpile, and then we're going to blend percentages of stockpiles so that we get a consistent gradation in our mix. Then once we mix it and dump it in the truck, there's another opportunity for segregation. Once we dump it in the paver, there's another opportunity for segregation. Once it goes through the paver, there's another opportunity for segregation. But the roller doesn't cause any segregation. Okay? So we got to watch for segregation very carefully. Dense graded asphalt, that's virtually everything you see. Okay? There's a rest area over in Maryland where the sidewalk has a sign on it that says it's porous asphalt. You have to kind of go to those extremes to find something in West Virginia, and actually you have to go to Maryland for that one. That's not dense graded asphalt. Okay, there are other ones, other states use others, we don't. We use dense graded asphalt. And so we're going to blend the stockpiles to get the proper gradations needed for the mix. The aggregate selection, we're going to make sure that we've got good quality product. Soundness, do you all remember soundness? Environmental deterioration, toughness, mechanical deterioration, and then deleterious materials. Turns out that if you make asphalt with a product that has 12% coal in it, it will fall apart.
I just want to ask this question before I forget. What causes potholes and roads? How does that happen? I always wonder.
Let's save that one to the end, because there's a lot of, I mean, it's not just, oh, too much trucks, oh, bad construction, oh, too much water, oh, freezing of the water, okay? It's all those. Okay, so we evaluate these properties for the stockpiles, and then we have what are called the consensus properties, and these properties are evaluated for the blend of the aggregates. Okay? So we said each stockpile is a good quality material. Now when we get the blend of the aggregates, do they have the properties that we want? These are these top 4 are the quality checks, and then these are things that we have to know in order to have a good asphalt. And of these, the hardest one to achieve is the fine aggregate angularity, but that's what gives us the stability of the mix. You think you've got the big rocks there, you put some sand, which is basically very round, it's going to act like ball bearings, you're not going to have a stable mix. Okay? So you have a test, and the test is meaningless unless you know what a bad number is, right? So fine aggregate angularity of 45, if we're doing heavy traffic, that's the minimum. That's a hard one to reach. Okay? We're only talking about national stuff right now. West Virginia's tuned this up a little bit. Our different mix types, the 475 down to 375, they're controlled by control points on a gradation curve. Basically, you covered those in the aggregate chapter. There is this thing called the primary control sieve, which determines whether or not the blend of aggregates is a coarse blend or a fine blend. That comes into play at one point in the mix design process. You have to compute your blended aggregate specific gravities. This is the equation you have to use. I don't know why. When I give a test on blended aggregate specific gravities, they think I'm messing with them, and they make up an equation. At least in class of 35, at least 2 or 3 students will make up their own equation. You get out in the 3rd decimal place an error, and so my test always has the opportunity to be creative, use the wrong equation. Of course, then your answer is graded incorrectly. You got to use this equation when you're blending aggregates. Bulk specific gravity is the volume of the aggregate plus the stone. Remember, G is for gravity, S is for stone, B is for bulk. Okay? We've got different specific gravities depending on which volume we're looking at. If we just look at the volume of the stone, it's apparent. If we look at the volume of the stone plus the voids that fill on the outside of the aggregates, the voids that can be filled with water. And if I give you a rock in that condition, can you tell me what that condition is? Saturated surface dry. Very good. But But then water molecules is H2O, right? That's a really small molecule. You think asphalt molecules are bigger? Pretty good chance. They're hydrocarbon chains. You can't have a few thousand carbons linked together. You can have tens of thousands. Now, if you start getting tens of thousands of carbons hooked together with nitrogen, it's going to be a big molecule. It's not going to fit in the same space as the water. So we have a difference in the absorption of the asphalt versus the absorption of the water. So we call this one the effective specific gravity. It includes the volume of the stone plus the volume of the void that cannot be filled with water. And that's the one we need to find out how much of our asphalt got absorbed, because the stuff on the inside of the rock isn't holding the stuff on the outside of the rock together. One of your big contractors in this area uses a lot of slag. It has high voids in it, and they buy asphalt to fill voids, and it affects their cost effectiveness. Binder selection based on temperatures, and so basically, if we start with a base temperature, base grade, and this is our West Virginia base grade, high traffic, all the interstates, all the 4 lanes fall into this category. We want to bump the surface material up to a 70 minus 22. Anything below 4 inches, we can go with a 64. Slow speeds, we should be using a 70 minus 22. Heavy and slow, Cole Hall route intersection, 76 minus 22. This requires that we add elastomers into it to make it more elastic, stretchable, okay? And so you start adding stuff into your asphalt, you're gonna start paying more for it, okay? So we don't want to overdo it, but we want to use it when it's appropriate. Okay, so the next thing we're going to do is we're going to determine our design aggregate structure. We're going to estimate an asphalt content. Now, engineers put this together, and somehow they have this whole process that we're going to talk about. And then at the end of the process, it says, use this process unless you have sufficient experience to where you don't need to use this process, okay? It costs $2 million to get in the asphalt business. You don't wait, if you've got that much money, you're not stupid. You don't wake up one morning and say, I'm gonna spend well actually there was one guy that did this and he's out of business. I'm gonna spend $2 million and I'm not gonna hire qualified people. So usually, you go to an asphalt plant, they got qualified people, they kind of blow by this step, but it's an official step in the design process. We have to determine GMM and GMB, right? And those are bulk gravity of the mixed bulk and gravity of the mixed mass, okay? We have to pick 3 aggregates that have a design aggregate structure. They have to fall within the control points and meet the consensus properties. That's what a design aggregate structure is. I just have one line on there, we would do it for 3, okay? We compact our mix up and we value for volumetric properties. It's a volumetric basis relationship between weight and space, or volume is what specific gravities are all about. For asphalt, we want 4% at mix design, 4 to 8% during construction, and we want at least 2% over the life of the pavement. Airport. Voids in the middle aggregate. Take a bucket, you fill it up with rocks, and the space you see between the rocks is the voids in the middle aggregate. For some reason, that seems to be a tricky concept. Well, then you're going to take it and put some asphalt in there. So the percent of the voids in the middle aggregate that you fill with asphalt is going to be your voids filled with asphalt, VFA. And then we have this check to see if the mix collapses too fast during construction. And then the dust, the stuff that's smaller than the number 200 sieves, 75 microns, really small stuff, it kind of acts different in the asphalt than aggregates do. It can actually act as an extender. And so we want to control that. And so we have what's called the dust to binder ratio. All these things are figured out on your equation sheet of what the process is. The top part of the equation sheet is some basic equations for doing aggregate stuff. And then this bottom is some more equations for doing aggregate stuff. The stuff over there on the left is the stuff, if you're going to make it up to asphalt and you don't have experience, you got to have a guess as to how much asphalt to use. So at the bottom left is the equations for guessing V is for volume, B is for, So look back if you need to. So there's where we're determining the asphalt content, and we have to do this for each design aggregate structure. Okay, the F has not been defined. Until you know better, use 0.8.
Wait, can you say that one more time? Assume F is 0.
Yep, 0.8 is close enough. If you're messing with slag, it's different, but only a few people do that. We're always going to mix design for 4% error. 4% error expresses the decimal fraction is 0.04. And then we have to have a guess of what the percent binder is. Down here, we're actually calculating it. Up here, we're going to guess it. And so a good guess to start is 0.6. The percent aggregate, the percents are based on mass. These percents are. The only one's not is based on volume with error. These percents are based on mass. So the percent stone plus the percent binder has to equal 100 because the error doesn't mass doesn't count. Okay? SN is your nominal maximum aggregate size, so we have 4.75, 19, 25, etc. And we just get down here and we wind up calculating a percent binder. It's not going to be the same as what we started with, so we have to use an iterative process. I always have my students set this up on a spreadsheet and use the solver in the spreadsheet. If you're doing it on a calculator, it should take about 3 iterations. Okay? So we have to do that for each design aggregate structure. Now we know how much asphalt we want to use. And so now we're getting, we're going to mix up some asphalt and we're going to make 2 types of samples. One is our bulk sample. It looks like that, the one I passed around except minus slice. And we're going to measure how much it collapses at a specific compaction level and what's the height at the end of the compaction. So we compare 2 of those samples and we compare 1 for the maximum theoretical analysis. And then we do the volumetric analysis. We have different compaction levels that we use for different traffic. This is the national standards. That's what's in your book. ESLs is just kind of a measure of the total truck traffic. If we had more time, we'd explain that. It's just total truck traffic. WDOH modified this table, and one of the points I wanted to make is you're always going to be working for a client or as a client. Make sure you know what the client's rules are. If you're in this town, that table changed. If you're in a town to the west, this is the correct table. And if you're a contractor, you're selling in both places. So back to our equation sheet, the volumetric analysis is the center column. Okay? So we take our samples and we analyze them. Now we wanted 4% error for, let's see. So this is just the equation, your ABCs for your specific gravities based on the different weights, and then the ratio of the bulk to maximum gravity. And this was compacted end design, so that's the end GMM, percent GMM at end design. Then we've got the percent GMM at end initial, where we get a printout with the change in height with as we apply more revolutions. That's got reduction there. Voids in the total mix, that's our air void. Okay? And so 1 minus the ratio of my bulk and my mass. Remember, bulk has air, mass doesn't. Okay? So that's my air voids. My voids in the middle aggregate, the actual space between the rocks, is computed as a function of the max of the gravity mix bulk, percent stone, and gravity of the stone bulk. Okay? And then our voids filled with asphalt is just basically the percent of those voids that we can see divided by the voids that are available. And then we have to get the aggregate effective specific gravity because we have to get down here and compute the dust to binder ratio, and it's really only the binder that's between the rocks that we're worried about, so that's called the effective binder as opposed to the absorbed binder. Okay? And so we just follow through this set of equations. And this is a variable that's not on your definition. This is percent stone, that works, but the 0.75 means it's for the 75 micron sieve or the 0.075 sieve, or if you're in the United States, it's the number 200 sieve. Superpay decided it wasn't in the United States. Okay, so we just get our various parameters. One thing to note, why is this PS showing up here? Is because binder absorbed divided by the weight of the stone. If we put the weight of the mix in here, we would change the absorption just by adding more asphalt to the outside of the rock. That doesn't make sense. Okay? So this is kind of a variance on the way we normally define things. Okay? Now we wanted 4% air voids. We go through the volumetric analysis and we find out that our samples didn't actually give us 4% air voids. So we do a mathematical adjustment, and that's on the right column, top right column. And we go through and we get an adjusted percent binder. How much binder would I need to get approximately 4% air voids? We get an adjusted VMA, VFA. By the way, pavement engineers love to talk in initials. My kids growing up didn't find out their name until they saw it written on their high school diploma. My son Lee was L, my daughter Anna was A, my daughter Krista was K. That's what they were. So we got VFA, VMA, percent GMM, NINI, PDE, and the dust to binder ratio, all just calculated using the equations. We compare those adjusted properties to our criteria. In your book, you've got a list of the criteria for each one of these. VMA is a minimum. It controls the minimum asphalt content that's going to be in the mix. VFA is a range, but if you put 4% air voids in the equation for predicting VFA, you'll find out that this lower range never controls during mix design. So VFA controls the maximum amount of asphalt you can put in there. VFA controls the minimum amount of asphalt. If they're all, if what you're looking for is at least one meeting the criteria. So for this one, let's see, number one, oh, it looks good. Number two also looks good. So you got two that meet the criteria. Which one do you pick? Whenever you go into construction, you always lose VMA. So at this step in the process, you always, if you have two that meet, you always pick the one with higher VMA. Okay, so now we know we've got a good set of rocks. How much asphalt do we actually want to use? So we pick up the percent, oh, whoa. I thought I got past this point. We pick up the percent binder that we got from the design aggregate structure. Right? We have our design aggregate structure, that's our blended aggregates. We make samples of 4 asphalt contents. The one that we picked from the design aggregate structure, a half below, a half above, and 1% above. We do the volumetric analysis. Exact same set of equations. These equations are all in your book, by the way, and there's an example of how to go through the equations in your book. This is just so that we can have it convenient. And maybe I shouldn't tell you this, but on my exam where there's asphalt questions, the students get this sheet. Oh, what are you looking at me for? I'm just telling you what I did. Wasn't a recommendation, wasn't a suggestion. Okay, then we plot the results for the 5 volumetric parameters. And we select the one with 4% air voids. So, and then we pick up our other volumetric parameters and we compare it to the criteria. So these are the plots we make. In every case, the percent binder is abscissa or ordinate. Which one's the horizontal one, the abscissa or the ordinate? Abscissa. I don't know how you remember, but if you say abscissa, your mouth goes horizontal, so that's the horizontal axis. Ordinate, your mouth goes vertical, so that's the vertical axis. Probably the only thing you'll actually remember 5 years from now. Okay. Our air voids, our VMA, VFA, percent GMM, NINI. Come into the air voids at 4%, pick your percent binder. Use that percent binder to pick your other volumetric properties. Read those off your chart because you don't have to make a sample of exactly 4% air voids. Put those into your table. And one of the things I always ask my students to do is summarize this stuff in a table. Don't just leave looking, oh, you got VMA over here and VFA over here. Put it in a table. I was in consulting 11 years. Hired a lot of young engineers during that period. That's one of the things that I expect them to do for preparing for clients. What's our criteria? What's our test results? Everything passes, so we have a successful mixed design. want to make sure that the asphalt doesn't collapse down too far, so we make a sample with that asphalt content, make a bulk sample and a max gravity sample. The bulk sample we're now going to compact to GMM, which is a simulation of the long-term traffic on the pavement, and we want a minimum of 2% air voids when we complete that. Okay? So, just doing the same process. Air voids is 1 minus percent GMM, so the criteria actually, I said 2% air voids, this says 98% GMM. In Morgantown, 1 minus 98, or 100 minus 98 is 2. Okay. Then we got to see, is it going to fall apart if we put water on it in traffic, and that's called moisture sensitivity. This is done with the tensile strength ratio test. I make 6 samples. I do the best I can to destroy the purity of the samples by conditioning, freezing, thawing, full saturation, sucking water into the voids, not just letting the sample sit there. And then at the end of the conditioning process, I measure the tensile strength by doing a dimensional test. If you squeeze the outside of the cylinder has to expand horizontally, right? Creating tension in the center. Best way you can do, if you got a material that's not good tension, it's hard to grasp it and pull it apart because it usually fails at the joint, at the grips. This, you don't have that problem. You can use it for asphalt or concrete. If you have more time, I'll tell you the origins of that test. Measure the tensile strength and compare the ratio. You want the strength of the conditioned sample divided by the strength of the unconditioned samples to be at least 80%. If you've done that, you've got a good product. If you failed that, then you can add anti-strip agents into the material, either liquids or powders, and improve the moisture susceptibility. It's kind of a big deal because if you get moisture susceptibility, you usually get it within a couple of years, and the asphalt just basically falls apart, right? If the aggregates aren't being held together by binder, they're just aggregates. We haven't said test this to see how good it is, and that's not in the super pave process. There's a new machine coming out, which is supposed to be called the simple performance test, but then they figured out it's going to cost over $80,000, so they didn't want to call it simple. And so it does this fancy testing. We don't really want to go into it. Got everything approved, sent to the highway department. They liked it. They said go ahead and build it. Then you got to have your materials plants. You got to have your aggregate stockpiles. You got to have your binder and your tanks. You have 2 types of plants where we mix up asphalt, batch plants, and drum plants. And then it has to be proportioned correctly, mixed, sent into trucks. Trucks can carry it to the job site. The trucks dump it into the paver, or there's another device that they can put in between it. The paver spreads it out on the surface and strikes it off so it's smooth. And then you can pack it down because coming out of the paver, it's only about 88% GMM, or what percent air voids?
Or right at 2%.
88. If it's at 88% GMM, what's the air voids? This requires that you subtract 100 minus 88, right? It would be 12 in Morgantown, I'm just checking. Okay? And so we got to get it up to a minimum of 92%. The plants, there's 2 types. There's a batch plant. This is the old style, where everything's broken down into batches, and it's kind of like making cake. A pound cake, you make a pound of butter, a pound of sugar, a pound of flour. You mix it all together, you've got 3 pounds worth of poison because carbs will kill you. That's another subject. So this does 1 batch at a time. A continuous plant, you squirt your aggregates in one end, they get dried out because we can't put hot asphalt on wet aggregates, right? It's kind of like throwing water onto a boiling pan of oil. Anybody ever done that? If you haven't done it, you don't have to do it yourself. There's a clip of the Mythbusters doing it, and it shoots flames 30 feet in the air. So we don't want to do that inside of here, right? Dry the aggregate, squirt the asphalt on it, but it's coming through continuously. So rather than being able to dump it in trucks, I've got to dump it in a silo, and then the trucks get loaded out of the silo. I want to be environmentally conscious, so the big things on the left there are the collectors. Separate the dust from the rest of the air so that they can release the rest of the air back to the population. Okay? Without this, dust is just blowing all over the place. Okay? Dump it in the trucks. Basically, the one we use on the standard dump truck, varying capacities. The advantage of that is maneuverable. The disadvantage is it doesn't carry much load. We get weight tickets at the plant. We deliver them to the inspectors on the job site, and so they see how much mix we're running out. We take the mix and we dump it into a paper. These are the base machine was developed in the 1930s. The mechanics of how this machine works was developed in the 1930s. Now, of course, it's all been updated electronically. Okay, but basically, these are pretty slick machines. You dump the asphalt in one end, it works its way through the paver, and it comes out being a smooth asphalt on the other end. If you've done everything right, the list of things you could do wrong is too long to be covered today. Then you got to compact it down, and we have multiple types of rollers we can use. But if you got a big roller and you start vibrating it up and down, you're putting a lot of energy into the paper. Okay? And that's what compaction is all about, getting energy into the paper. So the easiest way to get that energy is with a vibratory roller, and so it's got steel wheels on it, so we run over it, vibratory, smack it down. That first step is called breakdown. Next few times we run over it, it's called intermediate, and we may or may not turn on the roller or the vibrators for that. And then the last phase is finish rolling, and that's where we just want to smooth out roller marks. Sometimes you look at a pavement, you see like this little ridge on the pavement. You just have a big steel wheel on pressing down on hot asphalt. You know, if you don't come back and iron that out, you got a wrinkle. Vibratory, you can use it for finish rolling, just turn off the vibrators. Okay? So if you drive by a job site, this is what you're going to see most of the time. If you drive by one where they're running these vibrators, you'll feel it. It vibrates out. Several. Far enough that you don't have to be under the roller to feel it. You can be next to it. Big trick is getting it done in time. And so, depending on the environmental conditions, the temperature of the mix and everything, determines how much time we have to get the compaction done. Remember, we got the asphalt in there for two reasons. One, during construction, it acts like a lubricant. You let it get too cold, you're no longer getting the lubricant. Now that you're holding your rocks together and you smack it with this big machine, you're going to break rocks. You're not going to get further dense. So you have limited time to get density. Density. We want 92 to 96% of GMF. 4 to 8% air voids. What happens if you don't smack it to where you get where you wind up with more than 8% air voids? Study in Washington, they had pavements that they constructed really tight, and then they had other pavements that weren't that tight, and they evaluated how much life did we lose. Get to 9% air voids, you lose about 6% of your pavement life. Get to 10% air voids, you're losing, what is that, 18, 17% of your pavement life. You design a pavement for the last 12 years, it's now down to about 10 years. Big deal? 20% of your pavement value. You got 25,000 miles of pavements to pave, keep them in good shape. If you're getting 2 years less life because you didn't get it compacted right, you've increased the amount of work you have to do by 20%. Big deal. Write a specification, say 92% air voids is the minimum we'll accept. What does that mean? Or 92% is our requirement. What does that mean? 8% air voids. If I have a normal distribution of grades in this class, and the average score is 75, what percent of the class is getting less than 75? Half. If I specify 8% air voids and I pay the contractor's full amount because air voids are average 8%, how much of the pavement's going to have less life than what I want? Half. If I was writing the specs, I'd move that number up that way. And they're talking about it. The big key in getting this is to have everything in balance. Production of the mix, delivery of the mix to the job site, how fast we're putting the asphalt down, how fast we're getting it rolled. And the shame of this whole process is it's so easy to calculate. trucks in front of him, and then we'll have the rollers going too far behind. Two things that are really important about pavements. How long do they last? Doesn't get good density, we lose life. How smooth are they? Every time your paver stops and starts, it creates a bump or a sag. Every time. So you didn't bring your trucks out on time, the paver has to stop. The paver operator's not paying attention to what he's doing, he's driving faster than the delivery rate, he has to stop. They're not watching what's happening to the rollers, he has to stop to wait for the rollers to catch up, a bump or a sag. So density measurements, cores is the recommended way to do it. You just go down into the pavement, you slice off the part that you recently paved, you take it to the laboratory, do the bulk specific gravity test like we talked about for mix design, compare that to the GMM and you get density. But that takes a lot of work. We have nuclear gauges that can zap the pavement and tell you what the density is. Pretty good. Once you got it finished, compacted, and quality control, you can open it to traffic. Anybody see a problem with this slide? What's the problem? I mean, other than the obvious. Asphalt doesn't do this. Concrete does this. You see, if the picture quality was better, you'd see this is gray stuff on the tires, not black stuff. Okay? But it's a cute slide, so I decided to use it. Asphalt's really simple stuff, right? All you gotta do is design it, heat it, mix it, transport it, compact it, use it, and maintain it. But it is a particle reinforced viscoelastic plastic material. Now, I'm sure that in your engineering mechanics class, they taught you how to analyze that one. Probably not, right? They probably talked to you about a homogeneous, isotropic, heterogeneous, linear elastic material and all the equations you've had so far. That's steel. That's the simple stuff. Okay? This is where the problems get in. Because the car came in, I know he's interested in steel, that's why I said that. I got another story about steel, but we don't have the time. How much glue do we do in it volumetrically? We always are trying to use available materials. Rocks are cheap. Unfortunately, whoever the great maker is didn't put the rocks where we need them. The rocks that you're using in these plants along I-64, they were brought in from Indiana, some of them. Once you start transporting rocks, it's the transportation that's expensive. So we want to use local materials as much as we can. We've got severe environmental exposures. We've got complex dynamic loads. And we've got probably the most complicated material that we use in civil engineering. It rivals anything else. Thank you for your attention. I will say that I was impressed with your level of preparation from the previous chapters in the book. This was really fast. I know we covered a lot of material, but that was due to time constraint. If any of you are thinking about graduate school, our requirement is a 3.0 from an AVET engineering program. Got that? We'll accept you. If we have money, we'll give you an assistantship. Most students get those. It covers tuition, whether it's in-state or out-of-state, and it gives you enough money to live on. You won't get rich, you can buy beans. Okay? You can have a roof over your head. If you're interested in our graduate program, you can contact me or any of the specialists that you use. I would like my asphalt sample back. Oh, it's back there. Okay. Is there any other questions? I'll say and talk about potholes if you're interested, but I think the rest of you guys are interested. I won't take it as a sign of disrespect if you walk out and act like you're not interested.
It does appear there's another class there. You can just keep going if you guys want to. So, fantastic.